In this video, we're going to do some sample problems involving intermolecular forces and properties. So just a quick overview here. Make sure you review what the intermolecular forces are, their relative strengths, and when they occur, and be able to describe them. There's some great little videos that you can watch over here to give you that general overview if you need it. And please go back to previous videos and previous lessons to review that. It is an essential skill. A big part of understanding chemistry is knowing all the basic skills. So, for example, you need to know how to draw Lewis structures, Vesper structures, and use those to find polarity of molecules. And then from there, you can find what intermolecular forces are involved. And then from there, you can predict the properties. So if you don't have the basic first step, then it's hard to really climb those stairs if you're just trying to leap to the highest step without going on the first step first. So being able to identify the types of forces in molecules is the first skill that you need to be able to do the following types of problems that we're going to be doing. So I'm going to be going over these orally with some point form as well, but it's important that when you go through these yourself, you take a look at the answer keys that are provided in the slide deck that you can take a look at in the teacher visual. So here we have a great question. It's a great introductory question to explaining properties using intermolecular forces. So we have methane, which is a gas at room temperature. And then we also have water, and that's a liquid at room temperature. And so you'll notice that can be explained by their boiling points, essentially. You have methane negative 160, water 100 degrees Celsius. So water boils at a significantly higher temperature than methane. And you have to explain why that is using data from the table here. And so the more you know, the more you'll know what not to look at. And then that will help you to hone in on what you need to focus on. So you'll notice that their molecular masses are very similar to each other. They're not very different in terms of size. Methane is CH4, water is H2O. Now, if you didn't know that, you don't really need to know it too much for this question, but it's provided to you here. CH4, H2O, not too different in terms of size. So what does that mean? Well, that means that they have similar LDF. So they both have similar LDF because their size is similar. Water might have a little bit more, but LDF is probably not the reason why water is a liquid and methane is a gas at room temperature, and LDF alone is probably not the reason to explain this huge difference in boiling point. So what is different between them? Well, as you might notice, water is polar and methane is non-polar. I'm going to put NP. So water has both LDF and H bond, but CH4 has LDF only. And this is really the main difference between them that explains that boiling point. It takes more energy to break the intermolecular forces of the water, which is LDF and H bonding, versus that of methane. So in a question like this, you'd have to explain, well, first of all, they have similar LDF due to similar size. Secondly, what's the main difference then? That's going to explain why there's a difference of their state at room temperature. Well, one of them is polar and one of them is non-polar. And what does that mean? Well, that means that water has more LDF, has LDF and H bond, so more intermolecular forces overall, but CH4 only has LDF. So it requires more energy to break the IMF of water than CH4. It doesn't have to be extremely complex. You'll notice that this is kind of written in about 4 lines. Very straightforward. I answered the main question. You don't need to write big essays and big paragraphs. You can write a big essay and big paragraph all day long, and you won't get the right answer if you don't have the right information in there. So make sure you're answering the question that's asked by including the relevant information. There's no need to include more than you need to. So that was an essential, a basic introductory problem that you could see for explaining different properties of different molecules based on polarity and based on intermolecular forces. Here are some other problems you might see. So determine which of the following molecules experience dipole-dipole interactions and justify your answer. So for this type of question, you need to know What does it mean to be dipole-dipole? Essentially, that's when you have the partial charges attracted to other partial charges. And so a great example of that is when you have HCl interacting with another HCl. This is the dipole-dipole here. You have a partial negative Cl interacting with a partial positive hydrogen. And so that would be an example of a dipole-dipole. So really, to have dipole-dipole, you need to have polar molecules. You need to have polar molecules. If you don't have polar molecules, then you don't have dipole-dipole. So that's what I'm looking for here. Br2, is this polar? No, that's non-polar. It's one of those diatomics that has a delta electronegativity value of 0. It's a pure share. ICl, is this polar or non-polar? Well, you'd have to go look in your periodic table if you're not sure. So you can go to your periodic table, which we have up here. And a lot of these I'll be doing quickly because you have a general idea of how to do it. But Cl is 3, I is 2.5. So that's a bond that's going to be polar. If you do 3 minus 2.5, that's going to be 0.5, which is considered polar. And the shape overall is linear. So this is going to make this a polar molecule. So just to draw that out here to show you that, ICl. I didn't do the lone pairs, but I'll do them anyway just for completeness. The partial negative end will be where the chlorine is because it's more electronegative, partial positive where the iodine is. And it's going to interact with another one like this. This is the partial positive end. This is the partial negative end. And this would be a dipole-dipole interaction. This one here is nonpolar, so no dipole-dipole. HCl we just saw is polar, so there will be dipole-dipole. CH3Cl, so you'd have to draw that out and see if it's going to be polar or not. And if you use the flowchart for polarity, you'll find that this actually is a polar molecule with the partial negative being here, partial positive being here, since Cl is more electronegative. So this would have dipole-dipole. And then CH4, if you draw that out, you'll see it's only CHs. So we learned that from the previous video and lesson, that only CHs is nonpolar. So this would not have dipole-dipole. So you need to understand what the interaction is, what type of molecule is involved, polar. Knowing that, you can go find whichever one's polar, and then that essentially has dipole-dipole. Which experiences greater dipole-dipole interactions? Molecules of HCl or HI? Explain. So here we need to compare the two. We need to first of all see, do they both have dipole-dipole? Chances are they do, but you never know in a question. We got to check. So we want to check for polarity. We're going to check if these are polar. We know hydrogen's 2.1, chlorine is 3.0, and iodine, I believe, was, let's go back and check in our periodic table, 2.5. So here when we do our difference, we're going to get 3.0 minus 2.1 gives us 0.9. So definitely a polar bond. And here we'll do 2.5 minus 2.1, 0.4. So this is actually non-polar. I mean, it's really close to being polar, really close. So let's assume that, we're going to say that, it's not an equal, a fully equal share. Okay. Let's just pretend for a moment that it's so close to being polar that we'll consider it polar just for this question, just to make it happy. So both of these, let's just say, will experience some degree of dipole-dipole. Let's assume they both experienced some degree of dipole-dipole here. Which one would have the strongest dipole-dipole? Well, try to look at the more polar molecule. The more polar molecule will have the greatest dipole moment. Therefore, there'll be a more powerful, so to speak, partial charge, and that gives a stronger dipole-dipole force. So even though, yes, this is considered nonpolar, we'll assume for a second that there might be a little dipole region because it's not an exact equal share, but it still would not be as strong as the HCl. So in an answer like this, we'd probably say that the HCl has greater dipole-dipole and this is because HCl is more polar due to greater electronegativity difference. So you can show your work that you calculated the polarity, and you can then explain that HCl would have the higher dipole-dipole because of the greater electronegativity difference, making it more polar. So nice and simple, to the point, straightforward, and you don't confuse yourself by putting too many words in there. All right, let's try a few more practice problems. So I would recommend you always pause the video yourself first, try it yourself first, and then come back and check see if you're on the right track. And I'm going to try to do these ones a bit more quickly so you can see some tricks that I pick up on. Now notice that, again, we are just we're making these predictions. This could be wrong. Maybe this one has higher intermolecular forces. I don't know. It could be wrong. There might be other factors at play, but we're making predictions based on the information we know right now. And then later on, if we find there's something wrong, we can go and explain our incorrect predictions with other information that we may get. So it's important that you don't just Google stuff. It's important that you actually try to make predictions yourself first. So which of the following pure substances has a stronger dipole-dipole forces than the other? Provide your reasoning. So in each pair, we have to circle which one has the strongest. So in this case here, it could be a bit difficult to predict. But if we're talking about dipole-dipole forces, we saw that when you have HF, you can have a special type of dipole-dipole called hydrogen bond. So likely, the HF is the stronger dipole-dipole because you'll have hydrogen bonding. And it's also a more polar bond if you do the electronegativity difference. Water versus H2S. Remember, water is H2O. Water has hydrogen bonding, but H2S doesn't. So because it has hydrogen bonding, I'm going to say the dipole-dipole in the water is probably a little bit stronger than the dipole-dipole in the H2S. The nitrogen tribromide and ammonia, let's take a look here. So nitrogen tribromide, or ammonia, is this. And we know that we have an NH group here. So this is H bonding. Nitrogen tribromide is this here. And I just want to calculate the polarity of that bond just to see what it would be. It's not hydrogen bonding, but we have 2.8 minus 3.0. That's 0.2. These are non-polar bonds. These are all non-polar. But the molecule is still polar because of our lone pair up here. So it's still a polar molecule overall, but because the bonds are so non-polar, this likely will have very, very weak dipole-dipole interactions. So I'd go with NH3 being the strongest dipole-dipole because it has H bonding, whereas this does not even have H bonding. It's likely some weak dipole-dipoles because it's just slightly polar due to the lone pairs only. Now, that doesn't mean necessarily that this will have a higher boiling point because of the H bond. This might have, if you notice, and I'm just throwing this out there for you to think about, even though this doesn't have H bond, it's only slightly polar, this is a pretty big molecule. Like the Br has a big mass. There's a lot of electrons in Br compared to what N and H's would have. So maybe there's so many LDF there that it contributes to enough force to give it a higher boiling point. But we're not really asking that question here. We're really asking the question of which one has a stronger dipole-dipole in general. So hydrogen bonding, stronger than dipole-dipole, hydrogen bonding here as well, and hydrogen bonding here as well. And you can provide reasoning by explaining that there's hydrogen bonding occurring and in the others, there's not. Which of the following experience hydrogen bonding between their molecules? So it's really about identifying those special groups, the OH, NH, and HF groups. H2O, we know, has that. So there's hydrogen bonding. CH4 does not. No hydrogen bonding. HF has that. Great. HBr, there's no H, just wants to have fun in there. So there's none of these. So no. NH3, yes, H with N. CH3OH, OH right there. Yes, hydrogen bonding. And then CH3NH2, NH group right there. So hydrogen bonding. So you'll become quick at identifying these molecules, and you want to pick up tricks like that as you go. Okay. Which has the stronger hydrogen bonds between molecules, NH3 or H2O? So in a question like this, we can draw out just to show what it looks like. I don't know why I drew them in this position, but this is a partial positive, partial negative. Let's put our lone pairs there just to show that as well. This is a hydrogen bond between water. And over here, we'd have a hydrogen bond between ammonia and another ammonia. This is partial negative. This is partial positive. And the question is, which of these is stronger? The hydrogen bond between the waters or the hydrogen bond between the ammonia? So what I would do is I would calculate the polarity, the electronegativity difference for OH and NH. And I would try to see which one is more polar. So if we go to O, it's 3.5 and H is 2.1. So here we have 3.5 minus 2.1. That's a difference of 1.4 with the bond going towards the O, or the dipole going towards the O. For the NH, we have 3 for N and 2.1 for H. And so that's going to be 0.9. Still polar with our dipole going towards the N. You'll notice that the most polar one, though, is the OH bond. So because it's more polar, the dipoles are more pronounced, more partially negative, more partially positive than the NH dipoles. And so that would likely give the OH a stronger hydrogen bond capability than the NH. And that's usually the case. So in this case here, we're going to say that the OH has stronger, or I'll put H2O rather. I'll put HOH, the same thing as H2O. H2O has stronger H bonds than NH3. And the reason is the OH bond is more polar than the NH bond due to higher electronegativity difference in OH. So we just drew out a little sketch to show what the question was asking. Which one of these is stronger, this one or this one? We decided to check the bond polarity. And with the bond polarity, we're able to see that the OH is more polar. So therefore, the hydrogen bond in H2O should be stronger than the hydrogen bond in NH3. So that was some practice problems related to some dipole-dipole interactions, some LDF, and hydrogen bonding. Let's take a look at a few more questions involving LDF now. So here we have a graph or a table that has a bunch of different non-polar substances. These are all non-polar. And so I want you to spot the trend, and what you'll notice is that as the number of electrons increases, the boiling point increases, gets larger. The BP increases. And so the reason this is likely the case is because these are all non-polar. And so this is because the substances with more electrons have greater LDF, which makes it harder to disrupt those forces to evaporate them. And we saw factors that affect LDF, like the size and the shape. So you've seen that in the previous video. Here we want to figure out which ones experience LDF, and this is a nice easy one. Basically anything has LDF. LDF, 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 LDF. And then if it has other things, like it's polar, for example, then it might have dipole-dipole, hydrogen bonding. So if I go to water here, water has LDF plus hydrogen bonding. Sodium has LDF, and this is sodium metal. So there's metallic bonding in there too. CH4 is only LDF. HF is LDF and hydrogen bond. HBr is LDF and dipole-dipole. NH3 is LDF and hydrogen bond. This is LDF and hydrogen bond. This is LDF and hydrogen bond. So the next question is, which one has LDF only? Only. And so if you're asked which one has LDF only, you know it wouldn't be water because that has hydrogen bonding. You know it likely would not be Na because that's a metal and it has some metallic bonding in there. So we wouldn't do that. CH4 is nonpolar, so only LDF. HF has some hydrogen bonding in there. HBr has some dipole-dipole, I believe. If you do the, well, let's check. Let's double check that because I forget what the electronegativity is. 2.8 minus 2.1, right? So it's still polar. So there's dipole-dipole in there. So that's not only LDF. NH3 has hydrogen bonding. This has hydrogen bonding, and this is hydrogen bonding. So really, the only one that has only LDF is whatever is just purely nonpolar, like that. Or you might see like gases like argon, neon. These noble gases only have LDF in them because they're noble gases and they're just atoms. Determine the IMF present in the molecules below. If polar and H bonded to FON, there's hydrogen bonding. If polar and no H bonded to FON, then it's just dipole-dipole. And if non-polar, it's LDF only. So those are some guidelines that you can use. But basically, your first step is find out if it's polar or non-polar. This molecule is non-polar. Therefore, LDF only. This molecule here, you'll notice, is non-polar as well. Therefore, LDF only. This molecule over here, you'll notice, looks like it's going to be nonpolar, but because there's this different bond here, the CF here, this is going to make it polar. And if you calculate that, this is a polar bond. The whole molecule overall is polar. So we have a polar molecule. So there is LDF, but then there's also, it's polar, but there's no HF, HN, HO. So it's just LDF plus dipole-dipole. So similar type of question, determine the IMF present in the molecules H2O, H2, NH3, and HCl. And we have our similar rules there. But just to go over a couple of these, you know H2 is nonpolar, so it's LDF only. Let's do H2O. You know this is polar, so there's LDF, but you also know that it has the OH group, so there's hydrogen bonding. If you look at NH3, we've seen this molecule over and over again, but you know there's LDF for sure. Plus, it's the NH group, so there's hydrogen bonding. And in HCl, you know there's LDF for sure. You know it's polar, but there's no NH, HF, or OH. So because it's polar, it just has a dipole-dipole, but not the hydrogen bonding. We've done this question in the previous video. You can retry it yourself and go take a look at the previous video. And then we also did this question in the previous video too, predicting relative solubility. You can retry it and check that video there. And we also did this in the previous video, explaining why there was a difference in the boiling points. Let's try this one here. Similar question. So use London force theory to predict which of these alkanes has the highest boiling point, methane, ethane, propane, or butane. It doesn't really matter which. If you don't know what alkane means, the question is just asking which one has the highest boiling point and explain why. You'll notice these are all CHs. These are all CHs. So they're all nonpolar. So what that means is we must be looking at the one with the most LDF. And so the one with the most LDF is probably butane because it's the biggest one. So your prediction would be butane has the higher LDF or has higher boiling point. And your reasoning could be that butane is the largest, has more electrons, and therefore has greater LDF, which requires more energy to separate the molecules from each other and boil them. So provide your prediction, provide your reasoning. Largest, okay, well, what does largest mean? More LDF, great, that's why. Because it's larger, it has more LDF, which gives it a higher boiling point. Here we have another sample problem that you can try out, and I'm going to walk you through it. And you'll notice there's a variety of different ones, and the answers are revealed there as well. So we're going to finish off this video by just finishing off the problems that have to do with LDF and isoelectronic species. And after that, we'll go into problems that relate to other forces and predictions as well. So here we have a question that says, consider two isoelectronic substances, bromine and iodine monochloride, ICl. Based on your knowledge of intermolecular forces, explain the difference in their boiling points. So here we gave you the data. You have to look at the questions carefully. It says they're isoelectronic. What does that mean? Well, as a reminder, that means they have the same number of electrons. So what does this tell you? This tells you that they have the similar LDF. So that's probably not the difference in their boiling points. What is different? Well, if you look at the polarity, this is nonpolar. And if you do the polarity process, you'll see that ICl is polar. So ICl is polar and therefore has both LDF and dipole-dipole. But Br2 is nonpolar and has LDF only. So it's easier to break only LDF compared to breaking LDF and dipole-dipole. You can try this problem out yourself and check the answer out here. But essentially, try to use the previous one as a model to help you. It's written in a different way, but when you're doing this, make sure you practice how to word your answers. So which substance would have the higher melting point in this case, and explain. So make sure your answer really has sort of 3 lines at the most. Make your prediction, tell me the substance, explain why at the level of polarity, if there's a difference there, and what does that polarity mean in terms of forces to really hit home the point of your prediction. So 3 main points that I'm looking for there. So in this video, we saw several practice problems related to the properties and identifying forces. In the next video, we're going to continue in this slide deck here and do a few more practice problems related to the boiling points and forces and physical properties. And we'll do a few challenging questions in here as well.